Okay, hi everyone. Thank you to the International Workshop on Sustainable Road Freight for inviting us to present the results of our study. My name is Joanne Whitmore and I'm Senior Researcher at the Chair in Energy Sector Management at HEC Montréal. And I will be presenting with my colleague Clara Kayser-Bril, who is Director of Power at CPCS. The results of a study we did a few months ago on the decarbonization of long-haul trucking in Eastern Canada using the simulation of eHighway technology. So the reason we wanted to do this is, as is the case for many jurisdictions, freight transportation is one of the most challenging sectors to decarbonize. In Canada, it represents 8% of our national emissions, and it's tripled since 1990. It's a very complex sector because you have to take into account the logistic chain, the regulation, cross-border traffics. So it's definitely not an easy one, but at the same time, you have to also take in consideration the fact that the sector is key for our economic activity. So you have to do a transition that respects that. Current initiatives are insufficient to place Canada on a clear path towards emission reduction on road freight. We do have a carbon tax and different standards for the trucks themselves and some subsidies and clean fuel standards, but when we model all of this, it's still not enough to start curbing the trends in a way that's going to allow us to reach our 2050 goals. So this limits to the current initiatives has led us to consider other options because most of the options being looked at is hydrogen for trucks and as well as batteries. And on top of that, of all the other actions I just mentioned, but we haven't done real studies looking at eHighway, which uses basically the catenary system with overhead lines to power trucks. So we simulate the potential of eHighway technology on a real segment in highways in Eastern Canada between Quebec, Montreal, Toronto, up to the US border. It's about 1,300 kilometers in stretch. And for this simulation, we used data that's based on GIS analysis of current flows of heavy trucks according to the present capacity of the highways. So we wanted to stay as close and realistic as possible to the flows and volumes of traffic currently underway. And for this study, we just consider the hybrid diesel catenary electric truck, which is a hybrid system. So when it's on the highways, it's connected to the overhead lines, but then it switches to diesel when it comes out of the system to do the last mileage. But what's important to understand is that it's also capable of being a hybrid with other systems like natural gas, eventually perhaps hydrogen and battery, so it could recharge actually while it's connected to the grid. It can also restart the battery. So that's the 100% electric option is feasible. So the relevance of the technology in the Canadian context is that our linear transportation network is fairly linear compared to other regions, let's say like Switzerland. The other advantage is that our electricity, especially the power coming from Quebec, is clean, almost 100% decarbonized. Quebec has one of the largest public utilities of electricity in the world. And our electricity is fairly cheap, some of the cheapest also in the world. So if the technology is going to work somewhere, it should work here, given these advantages. But and also it's already been tested in a few in Sweden, so there's already some precedent. But what's the most interesting factor is the efficiency of the technology, given that it's a direct use of electricity, contrary to recharging of batteries where you have to wait and so on. And if we compare it with other technologies such as hydrogen and gas to power and battery, we see that on a wheel-to-wheel comparison, the efficiency is one of the highest. And the advantage that provides is that it allows to have more electricity to be used for other decarbonization measures, because obviously we don't want to just use electricity in order to clean electricity in ways to power the transportation, if we have to also decarbonize buildings sector and the commercial and industrial sector. So this is an efficient way to use our clean electricity. So the pilot projects that are currently ongoing are the ones taking place in Sweden since 2016, which has been a pioneer. They had a 2-kilometer project, pilot project, but now they're already looking or procuring one to be 20 kilometers. There's Germany that has also 3 ongoing pilot projects between 5 and 10 kilometers. In California, near Los Angeles, that's had a smaller road segment of 1.6 kilometers testing the technology. But what's most impressive is the explosion of planned projects or feasibility studies that are being looked, especially in the context of Europe, like in Germany, where the government's already looking for implementing 4,000 kilometers of eHighway by 2030. Sweden's considering 2,400 kilometers. There's also even India with over 1,000 kilometers of eHighway being considered, and multiple other interests in UK and so on. So with that, I will give the presentation to my colleague Clara to present the results of our study.
Many thanks, Joanne. So let me take you quickly through our methodology and results for a simulation of the eHighway technology. So we have considered a real-life corridor that connects Quebec City, Montreal, Ottawa, Toronto, and Windsor at the US border. Our objective was to use real-life traffic data. So the numbers that you see here is the number of truck per day recorded today on the highway. And we simply compared 2 scenarios, the business as usual, where trucks run on diesel almost entirely, and the eHighway technology in a specific configuration. As Joanne mentioned, it's a technology that can be hybridized with different energy sources. In our simulation, we have considered a truck that runs on electricity from the catenary when it is on the electrified segments of the road, and reverts back to diesel outside. But other technology combinations are possible. Of course, a large fraction of our work rested on techno-economic assumptions as regards how efficient and costly the eHighway will be. And as was mentioned earlier, there are some pilot projects, but that does not give us the cost of the technology if and when it reaches full commercial deployment. So we just did a review of the literature, and we came up with those key parameters. We considered that a truck needs 1.5 kilowatt hour of electricity per kilometer. That the infrastructure will cost 3.6 million Canadian dollars to build per kilometer. And then we looked at individual extra capital costs per truck, assuming that there will be a sharp decrease in the cost of fitting a pantograph on a truck from 70,000 to 20,000 per truck in 2040. As Joanne mentioned, we have electricity in Quebec as well as in Ontario that's pretty clean with very low carbon contents. And that is also quite affordable. And last important parameter was the value of carbon. So here we have followed the policy of the government of Canada, that is to increase from $30 per ton today, it's Canadian dollars, so $30 per ton today to 170 in 2030, and then we have assumed a flat value of carbon. So doing that, we have conducted several tests with our simulator. The first one was to see what happens if the infrastructure is deployed overnight and everyone uses it. So every heavy duty truck on the corridor switches to electric. And we have relatively good numbers in terms of simple payback period. So the number of years after which the initial investment is completely offset by the benefits that are the savings on fuel and the avoided CO2 emissions. We have an infrastructure that pays back in 9 years overall, and even much faster, 7 years for the densest part of the corridor that has more traffic. The second test we conducted was to look at a more progressive, more realistic deployment scenario. So we started where the traffic is densest between Toronto and Prescott, that is the gateway to Ottawa, and then Montreal, then to the US border, because as Joanne mentioned, there's a lot of interjurisdictional questions for a truck, for instance, that would start in Canada and continue in the US. So we consider it takes a bit more time to travel to the US with this technology. And then the last part to be electrified is the northern part where the traffic is less dense. So we also made assumptions, extremely conservative assumptions in terms of adoption by the industry, considering that at the beginning, only 0.2% of the heavy truck fleet would adopt the technology. Under these more realistic assumptions, we have, of course, a payback period that's longer. Here we have looked at the economic rate of return that ranges between 7 and 10%. Which is reasonable for that kind of extremely investment intensive infrastructure. We also note that it allows us to reach 2.8 million CO2 of avoided GHG emissions and 360 million Canadian dollars in terms of fuel savings per year. The last test we conducted was to test how sensitive our results are to various parameters, because we are discussing a technology that is under pilot testing, that is not yet commercially deployed, and we're testing it in a country that has even less experience. And we know from other projects that Canada is a relatively smaller market with a relatively more complex climate. So the cost may be higher typically in Canada as they would be in Europe, for instance. So what we found is that our results are obviously very highly sensitive to the cost of diesel. If diesel becomes more expensive, of course, the payback period will be much lower. It's also highly sensitive to the rate of adoption by the industry. And that's one key question for this technology. Is it suitable for the trucking industry? Is it compatible with how they operate and their constraints? And then the third most important parameter in terms of sensitivity is the capex of infrastructure. Obviously, if the infrastructure is more expensive, it will take more time to pay back. So our conclusion is that eHighway is definitely an interesting option. And as Joanne was saying, in Eastern Canada, we have cheap and clean electricity. So it really makes it an attractive option to be added to the other options that we have for decarbonizing freight. We also made a calculation of how much it would be in terms of abatement cost. So how much does it cost to avoid 1 ton of CO2? And we arrive at numbers that range from 65 to 200 tons of $200 per ton of CO2, which is not unheard of and rather attractive when it comes to decarbonizing heavy freight. But we still have many questions open. And the first one is, what would be the trucking industry's perception of the technology? Would it be compatible with how they operate? Is also the technology able to withstand the harsh winter that we have here in Canada? Yeah, it's been tested in Northern Europe, but would it work here? Also, we've tested it from an economic perspective. Looking just at the cost and benefits to the entire society, but what would be a proper allocation of the costs and benefits among stakeholders so that everyone benefits from it. And another question also is what would be the optimal design to maximize adoption and benefits? We have looked at one configuration with full electrification of the corridor and electricity plus diesel hybrids, but maybe there are other technological options that would make more sense and maximize adoption. If you want to know more, you are welcome to download the report on the HEC Energy website. Thank you very much for your attention.